Hey guys, Mr. Betts here. Let's take a look at a couple examples that use implicit differentiation. So in this first example here, we can see that we don't have a function y in terms of x, but we do want to find dy dx. So if we still want to find a derivative that tells us how fast y is changing with respect to x or the slope of a tangent line. So what we're going to do is we're just going to take the derivative of each term with respect to x. Remember, when the x is in the denominator here, we're going to take the derivatives with respect to x. So on the left side, when we take the derivative with respect to x of x, that's just a normal derivative. The derivative of x is 1, so that's just going to be 1. On the right side, when we take the derivative with respect to x, then we're going to run into something a little different here because the variable we're using is y. Now, with the chain rule, we don't have to deal with that y just yet. We're going to take the derivative of the mother function, the sine function, first. So we're thinking of this y as an inside function. And so we're going to take the derivative of the mother function. The derivative of sine is cosine. And we're going to leave the y inside. But then we have to multiply by the derivative of the baby. And in this case, since the baby function, the inner function is y, we're taking the derivative with respect to x. That means we're multiplying by dy dx. Now, the problem's asking us to solve for dy dx. So the next thing that we need to do is get dy dx by itself. And that's just a matter of dividing both sides by the cosine of y. So we have dy dx is equal to 1 over cosine of y. And I want to point out that normally, up to this point, our derivatives have all been in terms of x. So dy dx equals some stuff with x in it. It's okay with implicit differentiation because we're dealing with implicit relations that mix x's and y's together, not as necessarily as functions. It's okay that y is in our answer here. In the second example, not only do we want to find dy dx, but then we want to use it to find the slope of a tangent line. So specifically at the point 1, 2, we're looking for the slope of this tangent line right here. I like to kind of think of what our answer might be. It looks like roughly -2. Might be, depending on how well I drew it, maybe a little bit bigger, a little bit smaller than -2. So first thing, again, I'm going to do, this is in my head, I'm thinking we're taking the derivative of both sides with respect to x. We're going to have to use some other rules for differentiation here, specifically the product rule. So when I'm taking the derivative of this first term, we're going to have the 3x squared as the first factor and the y as the second factor. So the derivative of the first is 6x times the second, which is y, plus the first times the derivative of the second. Now we're taking the derivative of y, which is 1, but with respect to x, we're going to have to multiply by dy dx. So this one kind of seems weird that we would do this, but y is a baby function. So the derivative is 1, but then we multiply by dy dx. Then the second one, we're also going to have to use the product rule. So I'll call x the first and y squared the second. So derivative of the first is 1 times the second, plus the first times the derivative of the second, so times 2y. But again, that y is a baby function. Using the chain rule, we took the derivative of the y squared part, got 2y, times the derivative of the baby would be dy dx, equals, and the derivative of 10 is 0. Now we want to solve for dy dx. I'm going to go ahead and do this with multiple steps at once. So in my head, I'm thinking we're moving anything without a dy dx to the other side, or factoring out the dy dx, and then we're going to divide by what we factored out of the dy dx. So on the right side, we're going to get negative 6xy minus y squared. And then when we keep the dy dx's on the left, we're going to factor out the dy dx and have 3x squared plus 2xy. So we're going to end up dividing by that. And so we get dy dx is equal to all of that. Now, I did those steps in my head. There's nothing wrong with writing them. But essentially, when we're doing a problem like this, we at least need to get the derivative step right using implicit differentiation and then solve for dy dx. Now, more specifically, we want the slope of the tangent line at that point. So we're going to plug in 1, 2. So dy dx at, evaluated at the point 1, 2. So we're putting 1 anywhere we see an x, 2 anywhere we see a y. So we have negative 6 times 1 times 2 minus 2 squared over 3 times 1 squared plus 2 times 1 times 2. So simplifying, we got negative 12 minus 4 is negative 16 over, we got 3 plus 4 is 7, and we get negative 16 sevenths. We don't need to do anything else with that. We can't really do anything else with that. We definitely don't want to round it. So that's our answer. It does match with what I predicted earlier. I can see that I drew it a little bit off because my slope was a little bit less than negative 2. Actually, a little bit greater than negative 2, I guess. So it should have been a little steeper than negative 2, but we were pretty close. This problem didn't ask for it, but I do want to mention that a common problem is also to write the equation of the tangent line. So it's just one more step. So what we have here is the slope and the point of the tangent line. So we can use point slope formula, and we would have y minus 2 equals negative 16 over 7 times x minus 1. And that would be the slope, or I'm sorry, the equation of this tangent line right here. Again, this problem didn't ask for it, but that is something that you should be able to do.